All right. Today we are going to be talking about the response of general RLC circuits. So what our goal today is to analyze the following circuit, where we are going to have an 8 ohm resistor here, $10 resistor here, let's make this a 12-volt source. We'll have a 50 millihenry inductor here. A 20 ohm resistor here. And a 600 millifarad capacitor here. And lastly, up here at the top, we're just going to have a switch. And for this particular example, our switch is going to be closing at t is equal to 0. So this circuit does not fall into the category of a parallel RLC circuit or a series RLC circuit. If we looked at this circuit during the transient condition as a dead network, what we would have would be this. We'd have a 10 ohm resistor, short circuit from our switch being closed, our 50 millihenry inductor, our 20 ohm resistor, and our 600 millifarad capacitor. Hopefully from this drawing of the circuit during the transient condition, we can see exactly why I say this is not an example of a parallel RLC circuit and that it is not an example of a series RLC circuit, right? It's not a parallel RLC circuit because the 20 ohm resistor down in the bottom middle branch cannot be combined with the 10 ohm resistor because they are not connected in series and they are not connected in parallel. And it's obviously not a series connected circuit because the inductor, the capacitor, and the resistors aren't connected in series. So we are going to have to come up with some rules in order to solve circuits like this. And we are going to use our prior experience of solving series RLC circuits and parallel RLC circuits to figure out what to do. So as a very brief review, recall that for a parallel RLC circuit, let me draw a simple example of one here. Say for the sake of argument that our switch is going down like this. We have some resistor R, some inductance L, and some capacitance C, like so. we consider our voltage here across our parallel RLNC circuits to, or RLC circuit to be V of t, with this current IC of t, this current IL of t, and this current IR of t. Let's just call this VS and RS for the time being. When we derived our expression for a parallel RLC circuit, we wound up having a second order differential equation like this. This was our characteristic differential equation for our parallel RLC circuit. And for a parallel RLC circuit, we found that alpha was 1 over twice RC, and omega naught was the square root of 1 over LC. Now, I'd like to point something out here. Let's call this coefficient right here B. So that's the coefficient of the first derivative term. And let's call this coefficient right here C. And that's the coefficient of the 0th derivative term. Alpha is simply B over 2. And omega naught was simply square root of C. Now, let's talk about what happened when we had a series RLC circuit. Actually, let me make this switch open just for sake of argument here. Here's R, L, and C. Here's our current I of t. We defined VC of t with this polarity, the R of t with this polarity, the L of t with this polarity. And what we found is that this particular circuit had a characteristic polynomial. Second derivative of our current I of t with respect to time plus R over L times the first derivative of our current with respect to time plus 1 over LC times the 0th derivative of our current with respect to time was equal to 0. And we found that alpha was equal to R over 2L. And we found that omega naught was equal to the square root of 1 over LC. Looking at our coefficient for our first derivative term as B, and our coefficient for our 0th derivative term as C, we find that alpha is once again B divided by 2, and omega naught was simply the square root of our coefficient C. So effectively, if we can get a second order differential equation for our circuit where the coefficient of the second derivative term is 1, We can find alpha by simply taking the coefficient of the first derivative term and multiplying it by a factor of 1/2. And we can find omega naught by taking the coefficient of the 0th derivative term and taking the square root of it. Okay. So I'm going to scroll up here and we are going to make a copy of this circuit. And what we are going to do is we are going to figure out how to write a differential equation for it. So the first thing that I'm going to do to make my life slightly easier is, instead of using numbers here, I'm going to write my differential equation symbolically, okay? So I'm going to call this resistor R1, this resistor R2, this inductor L. Sorry, don't know what that is. This resistor will be R3. This capacitor will be C. I'm going to define some important figures of merit here. So this voltage, VL of T, is the voltage drop across my inductor. This current, IL of T, will be the current flowing through my inductor. Similarly, this voltage, VC of T, is the voltage drop across my capacitor. And this current, IC of T, is the current flowing through my capacitor. My goal here is to get an expression that is either second derivative of the voltage plus B times the first derivative of the voltage plus C times the 0th derivative of the voltage is equal to, let's just call it K, some constant, could be 0, could be a fixed number, or a second derivative of the form V squared DIL by dt squared plus B DIL by dt plus C IL E is equal to K. Let me make these VCs real quick. So effectively, I want a second order differential equation in terms of either the capacitor voltage or the inductor current. And from there, I can simply look at my coefficient B, look at my coefficient C, and then calculate alpha omega naught, and then move along with my day. Okay. So for T is greater than or equal to 0 plus, our circuit is going to look like this. When my switch closes at T is equal to 0, it shorts out the 8 ohm resistor. And I'm going to take a moment here to define my quantities of interest again with this representation. So here is VL of T, IL of T. Here's VC of T, here's IC of t. First thing that I'm going to do here, and there is no specific approach that we can take. We're just trying to effectively develop a few relationships and kind of see how things work out, okay? So the first thing I'm going to do here is I'm going to write a KCL equation at this top node. I'm going to have this current flowing in is equal to this current flowing out plus this current flowing out. Okay. My current flowing in is going to be the voltage drop over the resistor R1 divided by the resistance R1. And the voltage drop over resistor R1 could be expressed as Vs minus Vc of t divided by our resistor R1. My current flowing down through the branch containing the inductor is IL of t, and my current flowing down through the branch containing my capacitor is IC of t, and I'm going to set this equal to 0. Now what I'm going to do is a little bit of manipulation for this particular equation. So for example, I could say that negative Vc of t over R1 plus IC of t plus IL of t is equal to negative Vs over R1. That's just algebraic manipulation of our expression, where I'm moving the Vs over R1 term to the right-hand side of the equal sign. Now what I'm going to do is I'm going to express my capacitor current in terms of my capacitor voltage. And so what that's going to do is give me negative Vc of t over R1 plus C d Vc by dt plus IL is equal to negative Vs over R1. And I have this expression here in terms of only my capacitor voltage and my inductor current. So this is a good equation. So I'm going to call this one number 1. We might manipulate it further in a minute, but I've got it in a form that I believe to be usable because it's only in terms of my capacitor voltage, inductor current, and constants. Okay. So another thing that I can do here is I can write a Kirchhoff's voltage law expression around this loop. So let's call this KVL around the right-hand loop. And what I'm going to find is I'll have negative Vc of t plus VL of t plus R3 times IL of t equal to 0. I can then express VL of t in terms of my inductor current. So that's going to look like negative VC of t plus L DIL by dt plus R3 times IL of t is equal to 0. And this is another good equation because everything is in terms of the capacitor voltage and the inductor current. So I need to make a choice here as to what I'm going to do next, okay? So effectively, what my choice is do I manipulate that equation that I've labeled as equation 1 and isolate IL of t so that I can express IL in terms of VC and constants? Or do I isolate this second equation from my KVL at the right-hand loop, where I can isolate VC and express VC in terms of only my inductor current? Either way is going to get me the exact same differential equation. It's just one is going to be in terms of my capacitor voltage and the other is going to be in terms of my inductor current. It does not matter which one we choose. I am choosing to manipulate this KVL at our right-hand loop equation simply because algebraically it's going to be slightly easier because I don't have to carry that constant term around. That's the only reason I'm doing this. So I can say then, just by simple algebra here, that VC of t is going to be equal to L DIL by dt plus R3 times IL of t. So let's call this equation 2. And what this would allow me to do would be I could now substitute in anytime I see VC by itself with this expression in terms of only my inductor currents. Now, equation 1 has a derivative of VC term that I need to take care of. So what I can do is I can just take the derivative of equation 2 with respect to time. So that would look like the derivative of VC of t with respect to time is going to equal, bear with me while I go back and forth here so I don't make any algebraic mistakes. All right, so I'm going to take the derivative of the first term on the right-hand side. So the derivative of L di by dt is just going to be L times the second derivative by. Now I'm going to take the derivative of the rightmost term. So the derivative of R3 IL is going to be R3 times the derivative of IL. I'm going to call this equation 3. And now I'm simply going to substitute equations 2 and 3 into equation 1. So let's look back here. Actually, I'm going to make my life slightly simpler here, just because I'm having to do this. All I'm going to do is make a copy of equations 1, 2, and 3 and put them on the next page so that I have everything readily available. Here's equation 1. All right. Here's equation 2. And here's equation 3. All right, so I moved them all here so I could just see them while I'm doing my algebra. All right, so I'm going to have -1 over R1 multiplied by VC, where VC is L DIL by dt plus R3 IL of t plus C times the derivative of VC, which is L times the second derivative of IL plus R3 times the first derivative of IL plus IL is equal to negative VS over R1. And all I'm going to do now is I'm going to rearrange some things, okay? So for instance, I can see that I'm going to have LC times the second derivative of IL with respect to time from this term right here, right? Where I have L times the second derivative and it's being multiplied by that factor of C. That's the only time my second derivative term shows up. So I'm pretty well done with that one. Now I'm going to have plus. So we're going to look for first derivative terms here. Okay. So I'm going to have a R3 times C minus L over R1 times the first derivative and that's coming from this term and this term. And then for my 0th derivative, I'm going to have a factor of 1 from the rightmost term, just IL of t. And then I'm going to have minus, sorry, my page keeps moving on me, R3 over R1 IL of t, which comes from this term and this term, is equal to negative VS over R1. And now my last step is to simply divide both sides by LC so that the second derivative term has a coefficient of 1. So that's going to leave me with the second derivative by L with respect to time plus R3C minus L over R1, this whole coefficient divided by LC times our first derivative of our inductor current plus 1 minus R3 over R1 divided by LC times our 0th derivative of our inductor current is equal to negative Vs over R1 LC. This coefficient is B. This coefficient is C. So I can say alpha is B over 2 or R3C minus L over R1 times twice LC. And omega naught is always going to be the square root of C. So that's going to be the square root of 1 minus R3 over R1 divided by LC. Now let's take just a few moments here and plug in our numbers. So R3 was 20 ohms. Our capacitor value was 600 millifarads or 0.6 minus L, which was 50 millihenries, so that's 0.05 divided by R1, which was 10 ohms. And I divide this whole thing by L times, or excuse me, 2 times L 0.05 times C 0.6. And I get alpha to be 19.992 meters per second. Now I'm going to figure out omega naught. So that's going to be the square root of 1 minus R3, which is 20, over R1, which is 10. I think I'm about to run into an issue here that we'll resolve in a moment. Divided by L times C, so that is going to be let's see, 0.05 times 0.6. Yeah, so the issue that we just came up with is that effectively we're going to wind up having J 5.774 radians per second. Okay, so all that means practically is that we've developed an oscillator circuit. We have a not real angular frequency or not real resonant frequency. So we're gonna correct this. How we're gonna correct this is we're literally just gonna choose the value of R3 that's less than R1 so that this will come out to be a real number and make our life slightly simpler, okay? So just because of the random numbers that I chose, this came out to work poorly, or not really poorly, but beyond the scope of what we're trying to do in this class. So let's adapt this just very, very slightly. And let's change R3 from 20 ohms to 5 ohms. Okay. All that's going to do is make omega naught be a positive number, and it's also going to change the value of alpha, but it's not going to have any other effect on any of the math that we've done to this point. Okay. So if I replace that 20 with a 5, I get 4.082 radians per second. And if I replace that 20 with a 5 in my first equation, give me just a second to scroll through all this math here. So 5 times 0.6 minus 0.05 over 10 divided by, I get 4.992. Okay. So now our circuit is going to behave in a way that we can understand what's going on. Since alpha is greater than omega naught, this circuit is overdamped. And from here, we can simply go into all of our regular steps, analyzing the circuit at t is equal to 0 minus, analyzing at 0 plus, analyzing it at infinity, and then developing a equation for any of the parameters that we want. All right, so let's scroll back up to the top here. And let's decide a quantity of interest that we want to solve for. Okay, so let's see, Rajan, what do you want to solve for? And it doesn't have to be one of the 4 things I've listed. It could also be the voltage or current through the resistor R1, or the voltage drop or current through the resistor R3. The voltage drop across R3, okay? So this is what we are going to be solving for. This is our ultimate goal, V R3 of T. And so while we're at it here, we're going to think about what the easiest way to do this would be. I would argue that VR3 is just going to be R3 times IL of T. And so we're going to solve for IL of T and then use that result to calculate the resistor voltage that we're looking for. Okay. All right. So let me grab this real quick. Let's go through our circuit analysis steps now. So at t is equal to 0 minus, let's see what changes we're going to need to make to this guy. Okay, so at t is equal to 0 minus, our switch is an open circuit. Our inductor is going to look like a short circuit. And our capacitor is going to look like an open circuit. So we will have VC at 0 minus to solve for, IC at 0 minus to solve for, VL at 0 minus to solve for, and IL at 0 minus to solve for. So let's start with probably the easiest things. IC at 0 minus has to be 0 amps because it's the current flowing through an open circuit. And VL at 0 minus has to be 0 volts because it's the voltage drop over a short circuit. To get IL and VC, we're actually going to have to do a little bit of work here. Okay. Now, I would argue that the current that's leaving our 12 volt source is going to flow up through the 10 ohm resistor. It's then going to flow through the 8 ohm resistor, and it's then going to flow down through the 5 ohm resistor like so, because it can't split off. So the current that I've labeled in red is also representative of my inductor current. So from this, I can say that IL at 0 minus is 12 volts divided by 10 ohms plus 8 ohms plus 5 ohms is going to look like 12 over 23 amps. That seemed like a reasonable approach to determine that. All right. Now I can observe, I'm going to label some nodes here. So I have this node in green. And this node in pink. Our capacitor voltage VC is the difference in potential between the green node and the pink node, which is the same thing as the difference in potential or the voltage drop across our 5 ohm resistor, right? So using Ohm's law, sorry, it's too thick, VC of 0 minus is going to be 5 ohms times 12 over 23 amps is going to look like 60 over 23 volts. Any of that seem unreasonable? All right. Anybody in Zoom land having difficulty following the circuit analysis we're doing here? All righty. So I believe we finished analyzing our circuit at t is equal to 0 minus. So now let's move along to t is equal to 0 plus. So at t is equal to 0 plus, I'm going to copy the circuit again. And we're going to talk about what happens here. So at t is equal to 0 plus, our switch is now closed. And so I'm going to represent that by shorting out my 8 ohm resistor, effectively eliminating it from the circuit entirely. I'm going to replace my 50 millihenry inductor with a current source that is carrying whatever IL at 0 minus was, which was 12 over 23 amps. I'm going to replace my capacitor with a voltage source that's supplying whatever voltage I had at t is equal to 0 minus, which I believe was 60 over 23 volts. And we are going to be solving for all of these quantities at t is equal to 0 plus now. So let's start with the easiest things. Since the voltage drop across the capacitor cannot change abruptly, VC at 0 plus has to be the same as it was at 0 minus, or 60/23 volts. Similarly, since the current flowing through an inductor cannot change abruptly, IL at 0 plus has to be the same as IL at 0 minus, which is going to be 12/23 amps. And now I just need to solve for VL and IC. Okay. So let's think about things here. Okay. Now we could, if we were so inclined, wind up using nodal or mesh to determine what we're looking for. And there's nothing inherently wrong with that. But it can be overkill in some situations. So let me explain what I mean. Okay. So if we were to write a KVL equation around this loop, since we know how much current is flowing through the 5 ohm resistor, and therefore we know the voltage drop over the 5 ohm resistor, the only unknown quantity is the voltage drop over the inductor. Okay? So writing that KVL equation, we're going to have negative 60/23 volts plus VL at 0 plus 5 ohms times 12/23 amps is equal to 0. Well, 5 ohms times 12/23 amps is 60/23 volts. So from this, we can see that VL at 0 plus is still 0 volts. Now let's talk about how we might find IC. Well, I could say that this current flowing in is equal to this current flowing down plus this current, right? Or 12 volts minus 60/23 volts divided by 10 ohms is going to equal to IL, which is 12/23 amps, plus IC at 0 plus. And we can solve this for IC at 0 plus very easily. So 12 minus 60/23, all of that divided by 10 ohms, minus 12/23 is equal to IC. So IC looks like 48/115 amps. Anybody have any problems with the circuit analysis that we did there? All right. So now we're going to need to analyze our circuit at t is equal to infinity. Paste this guy here. At t is equal to infinity, our switch is still closed. Our inductor is now going to look like a short circuit because we're at DC steady state. Our capacitor is going to look like an open circuit because we're at DC steady state. And we're going to be solving for the following quantities, which are VC at infinity, IC at infinity, VL at infinity, and IL at infinity. By inspection, we can see that VL at infinity is 0 volts and IC at infinity is 0 amps. Using Ohm's law, much like we did to solve for IL at t is equal to 0 minus, we will have IL at infinity is equal to 12 volts divided by 10 ohms plus 5 ohms. So that's 12 over 15, which is the same as 4 over 5 amps. And using Ohm's law, VC at infinity is 5 ohms times 4/5 of an amp, comes out to be 4 volts. Any problems with our analysis at t is equal to infinity? No, pretty straightforward. It's almost identical to what we did at t is equal to 0 minus. All right, so we have solved for alpha, we have solved for omega naught, and we have determined that this circuit is an example of an overdamped circuit since alpha was greater than omega naught. We've analyzed the circuit at t is equal to 0 minus. We've analyzed the circuit at t is equal to 0 plus, and we've analyzed the circuit at t is equal to infinity. Now we need to use our response equations, right? So our inductor current, IL of t, will be of the form A1 e to the S1t plus A2 e to the S2t plus IL at infinity. We didn't find S1 and S2, so let's go ahead and do that. S1 is negative alpha plus the square root of alpha squared minus omega naught squared. So let me throw this into my calculator. So alpha was 4.992. Omega naught was 4.082. And so from this, I'm going to get, sorry, I was just storing things in my calculator. S1 is negative 2.119. And S2, which is negative alpha minus the square root of alpha squared minus omega naught squared, is going to come out to be negative 7.864. Second, and just storing things in my calculator for later use. All right, so IL, 4.992 IL at 0 plus is going to look like A1 plus A2 plus IL at infinity. Rearranging, we have A1 plus A2 is equal to IL at 0 plus minus IL at infinity. And using our values here, IL at 0 plus was 12 over 23. IL at infinity was 4 over 5. And so we're going to have A1 plus A2 is equal to negative 32 over 115 amps. This is equation 1. VL of T, which is simply L di by dt, will be of the form L times S1 A1 e to the S1t plus S2 A2 e to the S2t at t is equal to 0 plus. This looks like L S1 A1 plus L S2 A2. And so if I substitute in my numbers, so L was 50 millihenries, so 0.05 times the variable I have stored as C. I'm going to store that as A. Negative 0.106 A1. L 0.05 times S2, which I have stored in my calculator as D. Store the results of this as B, gives me negative 0.393 A2 will be equal to VL at 0 plus, which was 0 volts. If I'm recalling correctly, let's double check that. VL at 0 plus was indeed 0 volts. All right. And now I'm simply going to solve this system. So using my 2x2 system solver, my coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is negative 32 over 115. My coefficient for A1 in my second equation is negative 0.106, which I have stored in my calculator as A. My coefficient for A2 is negative 0.393, which I have stored in my calculator as B. And my constant term is 0. Solving this, I get negative 0.381 amps for coefficient A1 and positive 0.103 amps for coefficient A2. From this, IL of T is equal to negative 0.381 e to the minus S1, which, let's see, I think I have that as C, 2.119 T plus 0.103 e to the negative 7.864 plus, I believe it's 4/5. Let me scroll up here just to make sure. 0.8 amps. And finally, VR of T is just going to be 5 ohms times IL of T. So that's going to be negative 1.905 e to the negative 2.119 T plus 0.513 e to the negative 7.864 T plus 0.8 times 5 is 4 volts. Now, simulate our results. All right, so here's my resistor. Here is my voltage source. Zoom in here so I can make this nice looking. Let's wire these guys up. I'm going to have an inductor that goes here, another resistor that goes down here, a capacitor over here. My voltage is 12 volts. R1 is 10 ohms. L1 is 50 millihenries. R2 was 5 ohms. C1 was 600 millifarads. I'm going to put my ground at the negative polarity terminal of my capacitor. I'm going to label the positive polarity terminal of my capacitor. Let's see, the initial condition, so dot IC for the voltage at node VC came out to be 60 over 23. Since LT Spice, I do not believe will accept a fraction. 60 over 23 is 2.60869 volts. The current through inductor, sorry, I put the wrong parentheses there. L1 was 12 over 23, or 0.52174 amps. Let's start with a transient. Let's look for 5 seconds, let's say, and then we'll edit from there if we need to. We're looking for the voltage drop over our 5 ohm resistor, excuse me. It doesn't look like it settles in 5 seconds, so let's make this 10. Did not save my change. Okay. All right, that seems pretty reasonable. Now let's type in our results here. Negative 1.905. EXP negative 2.119 times time plus 0.513 times EXP of negative 7.864 times time plus 4. Alrighty, so that looks markedly different. Which means we've made a mistake. All right, so obviously this happens. It happened to me the other day as well. For this particular problem, it's going to be rather difficult to figure out where we made the mistake in the amount of time that we have left. So what I will do is I will hunt it down and let you know where the error occurred when we have class on Wednesday, before we start talking about how to handle two element, second order circuits that contains two uncoupled capacitors or two uncoupled inductors, because 10 minutes probably isn't enough time to figure it out. That being said, the process that we did here today is valid. So just to recap what we wound up having to do today, we developed a relationship for the response of general RLC circuits by, sorry, that was the wrong button, looking at what we had done for parallel RLC circuits and series RLC circuits to figure out what the relationship between our differential equation and our coefficients alpha and omega naught were. We then derived a second order differential equation for our circuit of interest using Kirchhoff's current law, Kirchhoff's voltage law, and a little bit of algebra and calculus, and solved for alpha and omega naught. We noticed that since alpha was greater than omega naught, we had an overdamped circuit. And then from here, we simply carried out our normal steps. Yes? So the curves weren't the same, so we know that there's a mistake. So from the shape of the curve, that's a good question. So let's look at this here. So from the shape of the curve, we know, generally speaking, that our overdamped response was correct, in as much as we don't see any ringing or oscillations or anything that would lead us there. Right, then it's very likely that we wouldn't have. Right. So yeah, I believe that that's probably an algebraic error somewhere. So the question is, I think what you're trying to say is, how do I figure out where the mistake was made? So like, was the mistake made when we were setting up our differential equation, or was the mistake made going through the steps? And honestly, for this, it's hard to tell. And the reason why I say that is because a simple mistake in setting up our differential equation wouldn't necessarily make our system no longer behave like an overdamped circuit. I'm gonna, excuse me, have to go through this literally line by line to figure out where the mistake was. And I'm gonna start with the differential equations because excuse me, that's where I believe I'm probably most likely to have made a mistake. That being said, if you watched Wednesday's lecture, I made a mistake with just units that mess things up here. So sorry, I've got a tickle in my throat. I'm going to go through line by line. The one thing that I would say though, when you're working with the differential equations, your best bet is to do things symbolically, because once you start throwing numbers in there, it's going to get very difficult to follow the algebra, at least in my opinion, or how my brain works. So I prefer to work with, you know, R1, R2, R3, L, and C, as opposed to putting the numbers in. Symbols, yeah. Right. And then plug the numbers in at the end instead of carrying the numbers along the whole way. That's how I feel. It's easier to do this difficult stuff. So that's what I would suggest that you do. All right, so like I said, we don't have enough time to actually go through and figure out where the mistake was made. So I'm going to take the time to do that before Friday's class. We will address the mistake and then go from there and talk about how to handle general RLC circuits. So I will see you all, general second order circuits. I will see you all on Friday.